All right, hello everyone and welcome. This is going to be my submission for the final project for Fundamentals of Game Engine Design. For this final project, I was trying to find something that would help prepare me for my thesis work in my master's program here at Ohio University. So I have been doing research on fluid and water body simulations, and I thought this might be a great opportunity to try and get actual practical experience with some of the methodologies they use to implement their surface simulations. So this is a paper from some researchers at Texas University or Texas A&M University, and it's titled Wave Particles. And this is a bit of an older paper. However, because of that, their computations are a bit simpler, and I thought maybe it might be a bit easier for me to grasp and actually get something implemented. So they use these things called wave particles that are spread throughout the surface of this body of water in this case to track motion and energy as it moves through the surface of the water. And then when this energy moves through a specific coordinate on that surface, they use a height field displacement in order to raise or lower that specific instance or those specific vertices at that location. So my overall idea was to try and implement some portions of this and see exactly how it worked. So before even beginning working on this, I've had very little experience with actual shader programming. So that was another bonus with getting to work on this, because most of this computation for these particles, since there can be hundreds of thousands of them, are done in a computation shader. So that would be a great experience to try and get my hands on this, or hands-on experience with working with computation shaders, because they're a huge player in many modern interactive graphics projects. So for my end goal here, I was able to implement a basic particle and height field displacement system. It's very rudimentary compared to what the researchers were able to complete. However, if we go ahead and run it here, this is first demonstration is with 32 particles, and all these are running on the computation shader. The surrounding area of each particle is in blue, whereas the actual main core displacement field of the particle is in a green or red. And you'll notice that when a couple of these go over each other, there's going to be a little visual issue, which we can cover here shortly. But the main idea is that each of these particles has their own energy displacement value, so they can displace the height field at a different amount. So you see that this guy right here that's moving really quick, it displaces the field a lot more than, say, this one over here, which is a very short displacement. And each particle has its own velocities and directional movements, and how quickly they move, their own velocities. So all of these are very independent of each other, and they all run in parallel on the GPU, and I don't know how well it turns up in the recording, but it is done in real time. So to get a little bit more crazy, we can go ahead and increase the number of particles. And we can talk about the little graphical bug that we saw earlier. All right, so we're going to go ahead and raise the number of particles here from 32 to 32,000. I had already messed with some pretty high numbers of particles, and we'll see exactly how visually wonderful it actually ends up looking. Spoiler alert, it doesn't look that great, but it is still kind of cool from a conceptual level. And we'll go ahead and let that build. All right, so this is it appears to be a visual mess. So, but if we zoom in here, we can see that there are still individual particles in this displacement field. Like this guy right here is one, and then these two are just colliding with each other. So the main issue that is causing all of this visual noise is with how memory writes are handled in the computation shader. When two particles are trying to, this is a single height field, a single texture, and every instance of the computation shader has access to the same texture and can write to any location in the texture. So when there are two particles that are trying to write to the same pixel on that texture, one of them can overwrite the other one. So that's why there's like this flashing effect. It's because one instance of the computation shader is writing slightly slower than the other one, causing one of them to write over the other one. So that changes from frame to frame, and each of these particles is moving a little bit. So for whatever reason, the differences of speed here is changing slightly. So one particle is alternatively writing over the other one, and they trade back and forth. That is a issue I wasn't able to finish or come up with a fix in time. That's just due to how memory management is handled on the computation shaders. So we'll change it to a more manageable size so we can actually look at it with fewer graphical bugs. So we're going to go ahead and cut it all the way down to 256 particles, just so that we can actually look at these behaviors a little bit closer without all the visual noise. There's still going to be noise because, they are still going to collide with each other. Right now, all of the particles are randomly generated. So their location, direction, energies, of course being bound by different ranges, are randomly generated. So, of course, there's going to be collisions, and it's going to be unavoidable at the time. But we can talk a little bit about how all of this works. So in the computation shader, we have the base height field. And this height field is what's going to be used, height field texture. And this height field texture is what is going to be used to actually displace the height field later on or displace the vertices later on in the graphics pipeline. So the base texture of this is a height field, which we actually, we can go ahead and we'll go ahead and pull up Nsight Graphics to demonstrate this a bit better. All right, so we're going to go over here to NVIDIA Nsight to try and show this off a bit, how this works. It should be noted that this actually, there's something wrong with how the shaders are linked with Nsight, and that causes the application to not work quite right, but we can look at the memory and what exactly is being bound and where, and that will help demonstrate how this works a bit. So it is a black height field, as I just said, with it not working quite right, but we'll go ahead and capture a frame, and we'll go to our computation shader dispatch, and we can look at the images that are being bound to this. So you can see that there's 3 images bound to this dispatch or to this computation shader. The first one here being a black texture, and this is the height field texture. This texture is written to by the computation shader for each particle, and each particle writes a different amount to the red channel of this. And the red channel is what is taken or read by the vertex shader, and the vertex shader raises the height of each vertex depending upon the amount of red that is in the texture at that time. So since the computation shader isn't running quite right with Nsight, it'll just be black, but as you saw before, there's going to be blue and different colors written to it wherever each particle is. The other textures we see here, the second one here, is going to look like jumbled mess. But this is actually the memory data for each of our particles. If we go in the memory read here, there are 4 channels in this first texture. And this first texture is the location and movement direction of each particle. So theoretically, these should all be within the range of 40 and 0, because that is the range of the height field. However, particles are permitted to move beyond the edge of the texture, and that was done because I wanted to avoid writing extra conditional statements, and that would, to better help performance. But that's something that can be addressed in a future revision of this if I continue to work on it. So these first two numbers are the positional location, x and y, and the second two are a movement vector, a normalized movement vector. Well, not normalized, but it's a movement vector for the direction of travel. It also can be used to, the magnitude of this can also be used to encode the velocity of the particle. However, for this specific version, the velocity magnitude was encoded separately, which brings us to the third texture, which is the energies. I call it the energies texture. So this is the second texture of particle information. So the first three numbers are the only ones being used in this. The alpha channel is all 0 because we never do use it. The first channel is the velocity magnitude of each individual particle. The second one is the energy, the displacement of the particle. This is the amount of height that a particle can add to each vertex, the maximum amount that it can write to. I think the maximum that I ever allow any of them to go to is 3, and I do see a couple getting up to 2, but none around 3. And then the third one, the blue channel, is all 1 for demonstration purposes. This is the radius of effect that each particle can have. Ideally, each particle should be permitted to affect a area rather than just one specific particle, or one specific vertex. Because in water movement, you don't just see little spikes coming out of the of the water surface. So this allows them to affect an area around the position where that particle is at. Because each particle is in a Cartesian coordinate plane. However, this is a float, we'll call it, a float representation of the location, so it has a decimal point. However, particle or texture coordinates don't really have, like for this height field, they don't really have decimal places. It's just whole numbers or integers. So to do that, to make that transition from that decimal space to the whole number space that is needed for the texture rights, the particle is sampled. So it's rounded down to the nearest whole number, and then the area of effect encoded in this texture, which right now everything is set to 1, will allow it to affect a area around that specific vertex. So we'll go ahead and take a quick look at the vertex shader and the computation shader, and I can run through just a little bit about how those actual functionalities work. So the vertex shader is pretty simple because I wanted to focus on the computation shader more than anything else. So the biggest thing is really in this little call right here, get height displacement from texture. This sets the changes the z position of the base grid to a different amount, and that is dependent upon the amount of red in the texture that is being read for this vertex. And that is since colors are an RGBA, the first element in that array is the red channel. So it takes that red channel, it's literally just the raw red channel, and adds that to the actual Z component. And since this is a base, or the base object of this is a flat two-dimensional grid that is all at a common height, theoretically 0, or whatever else I place it at, just adding red to a texture will allow a height change that is relatively different compared to its neighbors. So looking at the computation shader, each pass starts in the main function, and each position is from the global invocation ID for the instance of the computation shader that is running. Since there could be thousands of these running at once, each and every single one has its own unique X and Y coordinate, which is defined up at the top here, which is the amount of local invocations of each computation, or of each computation shader that can be run within a single work group. Because computation shaders are run in parallel, highly parallelized on the GPU, it is dispatched in what's called work groups. And each work group has an X and Y group size. Then each of those work groups can have a specific number of invocations per work group. So that is, the invocations are defined here, and the work group sizes are defined on the CPU side when we actually dispatch the compute shader. And we make the call to OpenGL to do that. For NVIDIA GPUs, as a side note, the best work group size is a multiple 32. Either way, we come in here and it reads, or it gets its main position. This is the position of the particle in texture memory. So of the two particle texture information that we saw earlier in Nsight, this is going to be the texture coordinate for that information for this specific particle that's running. So it goes ahead and pulls in these two vectors from that and generates a particle struct from those. And one thing to note is that since I never unbind the image data from the GPU, that image data is persistent from run to run. So it's really important to actually clear off the height field changes from the previous run, or else they will just stay there forever. And we'll just keep writing on top of changes that were already written before. So we have to make sure we erase or undo the changes that were done previously. And that's just done by writing black back to the texture again. So this is when we get into some nasty if statements. These are really terrible for shaders because it causes if one of these causes or takes a little longer than another one, it can cause the wave, it's called a wavefront computation, which is how the GPU handles the parallelized nature of shaders. If one part of this takes any longer than the other one, you'll get one part of the wave will be a little slower than the other part, a little bit behind. So that's where this barrier comes in. This barrier says, hey, we have to wait for all of the computations to get up to this point before it can all continue. And that's when we just apply the actual particle displacement, and that's from how much energy the particle has, how far away all the vertices are from that particle. And then we finally write out the updated particle information to the particle textures. This apply particle displacement is applying the displacement to the actual height field. This is storing our particles so that when we come back and run this computation shader again, the updated particle information, like its location, its energy, its velocity, all that stuff will still be there. And will actually be up to date because that's pretty important. Another thing to note is that there is a buffer here compared to the actual images. So the images contain, or our textures contain, all of the height field and particle information. It was really important to try and avoid reading and writing these to the GPU as much as possible because those kind of operations are pretty expensive. I wanted to make this as performant as possible. So that's why time is kind of an important thing when we want something to move with relative to real time. So I use a shader storage buffer for this, and these shader storage buffers are much easier to write to because they're a lot smaller and they're more efficient with reading and writing from the CPU to the GPU with this information. So it's just a double of the amount of time in milliseconds that has passed since the last frame call or frame draw call was made on the CPU side. So we'll go ahead and look at it one more time. But there is some promise here, and I am going to be continuing to work on this as I move forward with some studies in Vulkan, because this is just the very basic particle system of the actual paper that I was basing this off of. There's still a lot more to do with how particle information is translated from actual particle space onto the actual height field displacement. But the first place to actually fix for sure is these visual bugs when two particles overwrite each other. There are atomic operations available for buffer objects, but since this is the height field is a texture, that kind of operation isn't supported in OpenGL as far as I'm aware. So there are a couple options that I saw with how to fix this. So one of them could be an array of textures that represent the overall height field and allowing each particle to write to a different index in this array. However, this comes with overall more complexities with memory management and making sure I don't actually write beyond the size of the array. So as of now, that is a bug that is in this, but can be fixed in future work. But I think this lays a good groundwork for me to continue to work on particles and experience how cool computation shaders are, because we can max this at, well, not even max this, it can go even more, but we'll change it to back to the 32,000 particles on the surface, and we hardly see any performance impacts. It's going to drop a bit because I'm recording with OBS, but this is all running on an integrated GPU, and it is still well within real time at 32,000 particles. And for interest's sake, we'll go ahead and look at the GPU. It is maxing out its use. However, that is the integrated GPU rather than the my actual NVIDIA card, but that's with how this operating system chose, for whatever reason, to split up this work. But yeah, computation shaders are pretty powerful with doing the same operation on many different similarly structured objects. And I've seen experiments where people can get hundreds of thousands of these. And as long as your actual computations are efficient, it can do it well within real time. So this is a great thing to learn how to use if you're interested in parallel processing, or even working with particle systems in games or interactive graphics projects. But that is about it for now. Appreciate you watching, and we'll see you next time.